Hello everyone, my name is V. Ponsai Srinivas from CSIT B section. My roll number is C7. Today's my Tech Talk topic is a passive impedance matching concept for multiphase resonant converter. Subject BW Basic Electrical Engineering. Here we are going to the topic called a passive impedance matching concept for multiphase resonant converter. Introduction. LLC resonant converter has been widely used due to its high efficiency achieved by zero voltage switching, known as ZVS, on the primary side MOSFETs, and zero current switching ZCS on secondary side diodes. For high power applications, current stress of power devices increase with the power rating. So multi-phase parallel techniques is good choice to solve this problem. But component tolerances may cause each LLC unit to have different resonant frequencies. They will lead to the deviation of current stress in each LLC unit. Small component tolerances will cause large current imbalance. Thus, the key problem is load sharing. This is the example for LLC resonant converter. Three technologies have been used to achieve current sharing in multiphase LLC converter. First method, active method. Passive component tolerance can be compensated by adjusting the variable capacitor or inductor in an additional circuit. Advantages for this method is perfect load sharing performance. Disadvantages for this method is large cost, complex control, and non-excellent dynamic performance because of sensing the circulating current and control the additional switches. Second method, self-balanced DC voltage. It is based on series bus capacitors. Advantages of this method is low cost and good load current sharing performance. Disadvantages for this method is it has poor reliability, hard for modularization design. It is the example for the self-balanced voltage. Third method, built-in three-phase, three-wire structure. It is only used for three-phase LLCs. Advantages of this method is good load current sharing near resonant frequency as all of three-phase resonant current is zero. Then, a passive impedance matching concept is proposed for multi-phase resonant converter. A passive element such as an inductor or a capacitor is put in the common branch of the multiphase units. A set of virtual resistors, or known as positive and negative, are yielded through the common branch inductor or capacitor, which changes the gain curve in different converter. Virtual impedance concept. In figure 1 shows the basic circuit about common branch impedance. In figure 1a shows that K current source units I1, I2 up to so on Ik in parallel are connected to the common branch. The voltage of common impedance Zs is Vs. The total current is defined as Is, where Is is equals to the sigma Ij. In figure A is common branch, figure B shows the equivalent circuit. The impedance Zs can be separated into Zs1, Zs2, so on up to Zsk for each element based on current I1, I2, so on up to Ik to achieve virtual open multiphase units, which is shown in figure 1b. Three kinds of passive elements like inductors, capacitors, and resistors can be selected as impedance Zs. Resistors will introduce power loss and lower efficiency of converter. Thus, inductors and capacitors are better candidates in this application. Figure 1c and Figure 1d illustrate two examples of sharing on inductor and a capacitor in the common branch. Figure 1e is the vector plot of sharing on inductor in Figure 1c. Vector Is is composed of vector I1 and I2. The current I1 is leading current I2. So the impedance angle of Zs1 is smaller than of Zs2 is larger than 900. In consequence, impedance Z1 is equivalent to an inductor K1 Ls and a positive resistor Rs1 connected in series. Similarly, impedance Zs2 is equivalent to one inductor K2 Ls and a negative resistor R2 connected in series, where K1 and K2 is the coefficient parameters there can be found in second equation. The circuit in figure 1c can be replaced by the circuit in figure 1g. In the same analysis, two separated impedance can be given by virtual open. The circuit in figure 1 can be replaced by circuit in figure 1h, where K1 and K2 is the coefficient parameters. In second equation, we will know about the S into K1 Ls plus Rs1 into SK2 Ls plus Rs2 divided by K1 plus K2 whole into SLS plus Rs1 plus Rs2 is equals to SLS. In equation 3, it shows about the 1 by SK1 into Cs plus Rs1 whole into 1 by Sk2 Cs plus Rs2 whole divided by 1 by K1 plus 1 by K2 whole into 1 by Scs plus R1 plus R2 is equals to 1 by Scs is the equation 3. No matter for the sharing inductor or capacitor on equivalent circuit with virtual positive resistors and negative resistors can be always derived. Three different LLC converters with variable resistors will be analyzed. In figure C, it is sharing inductor. In figure D, it is sharing capacitor. Analysis of three LLCs with variable resistors. From the analysis in the above section, the common branch impedance is equivalent to the new impedance network with virtual positive resistor or negative resistor. For easy understanding, LLC resonant converter is made as an example. Three LLC converters with virtual resistors based on different common branch will be analyzed next. The first common branch is series branch, the second one is parallel branch, and the last one is a primary side branch of the transformer. The gain expression of the first LLC converter with resistor is shown below. GDC is equals to NVA by VM divided by 2. That is equals to modulus of V1S by V total voltage of total circuit. That usualized to under root 1 by under root 1 by M Fr by Fs whole square minus 1 plus Mk by M whole square plus 1 by Kmq plus Q whole into F by Fx minus Q into Fs by Fr whole square, where Q is equals to under root Lr by Cr 1 by R naught into Fr 1 by 2 pi whole root R Lr Cr where M is equals to L by M by LR, where RA is equals to 8N square by pi square R naught, where K is equals to RS by RAC, where F is equals to Fs by Fr. In figure 3 shows gain curve with the different switching frequencies. First one, K equals to 0 represents the traditional LLC converter gain curve. Say point 2, K equals to 0.05 represents an LLC converter with a positive resistor. Point 3, K equals to minus 0.05 represents an LLC converter with a negative resistor. The gain value reduces significantly when K increases from 0 to positive at switching frequency Fs1. Likewise, the gain value increases significantly when K decreases from 0 to negative at switching frequency Fs1. Thus, adding virtue resistors to the series branch can improve the performance of load current sharing significantly. This is the gain graph where graph is plotted from 0 to 3 and 0 to 3,000 3,50,000. The graph significantly increases, then mutually decreases. A. First, LLC converter with variable resistor. Figure 1 shows the first LLC with a virtual resistor Rs. If the value of resistor Rs is 0, the converter in figure 2a is traditional LLC converter. Figure 2b shows the equivalent circuit based on fundamental harmonic analysis. In figure A, first LLC converter with a virtual resistor. Figure B shows the FHA equivalent circuit. B. Second LLC converter with variable resistor. Figure 4 shows the second LLC with a virtual resistor. A resistor Rs is added into parallel branch. If the value of resistor Rs is 0, the converter in figure 4a is a traditional LLC converter. Figure 4b shows the FHA equivalent circuit. The gain expression of the first LLC converter with a resistor is shown in phi. In phi, GDC is equals to NV0 by V in divided by 2. That is equals to modulus of V1S by V in S. That is equals to uh, under root m square fs by fr whole power 4 plus k square q square whole into fs by fr whole square whole divided by under root 1 plus k minus 1 plus k plus m into fs by fr whole square total whole square plus fs by fr into q k by q plus mq minus mq by fs into fr whole square where q is equals to under root lr by cr by r naught, fr is equals to 1 by 2 pi under root f lr cr, where m is equals to lm by lr. RAOC is equals to 8n square by pi square into R naught. K equals to RS by RAC. F is equals to F by FR. In figure A, it shows about the second LLC converter with the virtual resistor. In figure B, it shows the FHA equivalent circuit. C. Third resonant converter with variable resistor. A CLL resonant converter has been reported and it has similar performance with the traditional LLC converter. A CLL resonant converter has a passive inductor in the primary side of the transformer. Thus, this topology can be used to build virtual resistor for multiphase CLL application. Figure 6 shows the second LLC with virtual resistor. A resistor Rs is added into parallel branch. If the value of resistor Rs value is 0, the converter in figure 6a is traditional LLC converter. Figure B shows the equivalent circuit based on fundamental harmonic analysis. The gain expression of a first LLC converter with the resistor is shown in 6. GDC is equals to NV naught divided by V in divided by 2. That usualized to modulus of V1S by V in S. That is equals to Fs by Fr whole square whole divided by under root 1 plus k by m minus 1 plus k Fs by Fr square whole square plus m minus m q into Fs by Fr whole into 1 minus Fs by Fr square whole square. Figure A shows about the third LLC converter with the virtual resistor. Figure B shows about the FHA equivalent circuit. This is the gain graph for the C application. Fourth one, experimental results. A 600 watts two-phase LLC converter in section 2 is built to verify the feasibility and demonstrate the advantages of the proposed method. Figure 8a shows two-phase LLC resonant converter sharing series inductor. Figure 8b shows FHA equivalent circuit based on Figure 8a. According to passive impedance matching concept, the equivalent circuit based on separated impedance is shown Figure 8. In this figure, it shows about the two-phase LLC with the first common branch using inductor. The gain value reduces significantly when k increases from 0. The gain value increases significantly when k decreases from 0 to negative. In this situation, adding virtual resistors can improve the performance on current load sharing. A virtual positive and negative resistor R1 or R2 are added into series branch. From FHA circuit at figure 8D, two-phase LLC converter shown in figure 8A has been transformed into figure 8E. The virtual resistor R1 and R2 have a different sign. The resonant current sharing error is defined as follows. Resonant error is equals to RMS ILR1 minus RMS ILR2 divided by modulus RMS ILR1 minus RMS ILR2 modulus. Figure B shows about the FHA equivalent circuit. Figure B shows about the equivalent circuit based on separated impedance. Figure D shows about the equivalent circuit with independent impedance. Figure E shows about the equivalent two-phase LLC converter with virtual positive and negative resistors. To express the resonant current sharing error between the two-phase according to the 7, the resonant current and resonant current sharing error are shown in figure 11. Figure 12. The current sharing performance is better with the load increasing, which is usually parallel operation. The resonant current sharing error reduces 63 times and is only 0.44 at 600 watts total load power. Circulating current is significantly reduced using PIM multiphase resonant converter. In table 1, it shows about the prototype parameters. Switching frequency, input voltage, output power, transformer ratio, N. This is the information about it. In figure 9, A is steady at 180 watt load and B is steady at 300 watt load. In figure 10, B is steady at 300 watt load, C is steady at the 600 watt level. In figure 11, it the graphs of resonant current of two-phase conventional LLC converter. In figure 12, it graph shows the resonant current of two-phase proposed LLC converter. From the above graphs, it is stated that it shows the resonant current waveform at 180 watts and 300 watts operation with the purpose method. The resonant current ILR1, ILR2 are more almost same. This is the information about the passive impedance mutual exchange resonant converter. Thank you for the opportunity.